Hello everyone. In this particular video we will be looking at related rates exercises. So without further ado, a stone is dropped into a still pond and sends out a circular ripple whose radius increases at a constant rate of 3 feet per second. The question is, how rapidly is the area enclosed by the ripple increasing 10 seconds after the stone hits the pond? Well, in order to understand what the heck is going on, I think first we need to get down some sort of equation, and that being the area of a circle. So the area of a circle is in fact A equals pi r squared. And we want to fill in as much of this equation as we can, but right after we find out what the derivative is. So I see a rate here, a rate of 3 feet per second. Let's go back and see what that is. See, the radius is increasing at 3 feet per second. So any rate will be how the radius, or how the variable is changing with respect to time. So how does the radius change with respect to time? This will be 3 feet per second. And that's great. So what we're trying to figure out is how the area is changing. How rapidly is the area increasing? So we're trying to find this dA over dt as the goal. So with that, I think we can go ahead and take the derivative of this particular function. And so I'm going to go through and take the derivative just like we normally would with any variable. This is to the first power, so I would move that 1 to the front and subtract 1 from the exponent, so this left side would be 1. But since we're taking the derivative with respect to time, I will need this dA dt here equals pi, the derivative of r squared would be 2r. But I'm also taking the derivative of r, the radius, with respect to t, so I will have dr dt. dr dt. All right. So I'm just going to clean this up a little bit. The 1 times dA dt can just be written dA dt equals 2 pi r dr dt. I just like seeing that 2 first in front of the pi, so I moved it there. So now we can start filling values in. So this 3 here for dr dt, I'm going to go ahead and fill that in for dr dt. And so we have dA dt equaling 2 pi r times 3. And this, now you can see we have a problem. We're trying to find dA dt, that's fine. 2 pi is a constant. We're able to substitute 3 in for dr dt. But r, we have no idea what r is. It doesn't say here the radius is anything. But what we do know is that the rate that the radius is increasing is 3 feet per second. And we know that it has been increasing for 10 seconds. So what that means is we can find if the radius, if it's increasing 3 feet per second for 10 seconds, we know that the radius should be 30 feet. And so we can use this 30 here in for r. So when you multiply 2 times 30 times 3, 2 times 30 is 60 times 3 is 180 pi. So dA dt, the area is increasing at 180 pi, we'll say feet squared per second at this particular point in time. A 13-foot ladder is leaning against a vertical wall. If the top of the ladder slips down the wall at a rate of 2 feet per second, we will have 2 questions here. How fast will the base of the ladder be moving away from the wall when the top of the ladder is 5 feet above the ground? So in this picture here, I have a nice little setup where this is the actual ladder. and the ladder is 13 feet. The next piece is, we know this side here is 5, and if you use the Pythagorean theorem, this last side of the right triangle seen here, formed by the wall, the ground, and the ladder, is 12. So now, those are all of the actual lengths. If we can find the rates, why don't we call this side A, this side B, and this side C. That way it sort of fits the Pythagorean theorem there. And we can set up an equation actually here. So we will have a squared plus b squared equals c squared. And I'm using the Pythagorean theorem because I see this triangle here. And let's see, what can we say about the different rates? The different rates, we have the ladder slips down the wall at a rate of 2 feet per second. So that means the rate here for A, we'll say dA dt, is negative 2 feet per second. And that's because that distance is getting smaller. It is a decreasing distance. So that being said, we are trying to find out how fast the base of the ladder is moving away from the wall. So our goal here is to find dB dt. And you might be wondering to yourself, well, what about dC dt? How fast is this distance changing? The length of the ladder. Well, the length of the ladder isn't changing. It is what I would call static. It's constant. So the dC dt here, dC dt is 0. So when we find the derivative of this particular equation, it is 2a dA dt, then 2b dB dt equals 2c dC dt. And this entire right side of the equation becomes 0 because dC dt, as we just mentioned over here, is 0. But we can go ahead and substitute everything else in for all these other pieces, parts, and the equation will look something like this. And then all you have to do is solve for dB dt, as that is our goal. So that means we just multiply all this together, get negative 20, add it to both sides and get 24 dB dt equals 20. And then to divide by 24, we will have dB dt equals 20 over 24. And you can divide both of those by 4 and get 5 over 6. And since these distances are being measured in feet, and we are finding a rate, this would be feet per second. So there's part A. Part B deals with the angle that is formed between the ground and the ladder. So this angle right here, theta. And what we can say here is that the cosine of theta would be what you get when you divide B, the adjacent side, by C, the hypotenuse. And so we can go right into finding the derivative. All of these values for this second scenario, part B, still are in effect. So dA dt is negative 2, A is 5, B is 12, C is 13. dB dt we now know as 5 over 6, and dC dt is still 0. So when we run through this derivative of the quotient, really quickly. We will get the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. This entire second term is 0 because dc dt that's here is 0. 0 times anything is 0. So we just have to worry about this side. And on the left side of this equation, we have a negative sine of theta d theta dt. And this is what we're after right here. So to simplify this side a little bit, we could then, after we turn this into 0 because dc dt again, we can cancel a c here. So the right side of this equation simplifies even further to db dt over c, and that will equal negative sine of theta d theta dt. And I think at this point we can just start putting values in. So dB dt we found here is 5/6. C is 13, is right here. But negative sine of theta, let me catch up here, 5/6 over 13. And negative sine theta, well, we can just come back to this triangle here and look at the opposite over the adjacent. So that would be 5/12 for the sine, and this negative is here, so it would be negative 5/12 d theta dt. Now this side, if I want to simplify here a little bit, will become 5/6 times 13. So just a quick rewrite of this will show negative 5/12 d theta dt equals 5/6 times 13. Lastly, I want to multiply by the reciprocal of this thing, so I'm going to multiply by the negative 12/5, and these 5's will cancel, and this 12 will reduce with the 6 as a 2, and so d theta dt will be negative 2/13, and theta is going to be measured in radians per second. Last one for this video. We have this problem: wheat is poured through a chute at a rate of 10 cubic feet per minute and falls in a conical pile whose radius is always half the altitude. How fast is the radius of the base changing, I guess increasing, when the pile is 8 feet high? So here's the scenario. We have this chute dropping wheat on this perfectly conical pile of wheat. And let's see, I think it would be really great if we could find a way to look at the volume of this cone. So the volume of this cone can be found by using the equation 1/3 pi r squared h. Now, just so that I can say it and everybody's clear, the volume of a cylinder is pi r squared h. So that is the area of the circle at the bottom of a cylinder times the height. And there are proofs out there in the internet that you can find, probably even on YouTube, that you can find that explain why the volume of a cone is just 1/3 the volume of a cylinder. But we're not worried about that. What we are worried about here is finding how fast the radius is changing. So we have this radius that's here going to any edge of the circle r, And we want to find out how fast dr dt is changing, especially, most specifically, when the height of this cone, or the altitude, if you will, is 8. So there are a few things we know: that if the height is 8, then the radius is 4. And we know that because it says up here, let's see, the radius is always half the altitude. So we know that the radius is 4 because that's half of 8, aka the altitude, aka the height. That also gives us the equation that the radius is 1/2 the height. And that's super important because when we try to find the derivative of this equation here in a little bit, we will want this all to be one variable. And in fact, we want this to be in the variable v, written in terms of r, in the variable r, because we're trying to find dr dt. If I were to substitute this 1/2 h in for r, and we take the derivative, we would get how fast the height is changing. And we are not after that. We're after dr dt. So really, I think I should have this say h is equal to 2r. If you multiply both sides of this equation by 2, you get h equals 2r. And so I like that moving forward because I can substitute this in for h, and then the equation on the right-hand side, anyway, will be all in the variable r. So why don't we go ahead and do that really quickly. This will be v equals 1/3 pi r squared times 2r. So what that leaves us now is, wait, do we have all of our information? No, it looks like we have this little bit here. Wheat is being poured through chute at a rate of 10 cubic feet per minute. So that cubic feet unit, that means we are talking about a volume. So the volume here is changing at a rate of 10 cubic feet per minute. But it's a positive 10 because this pile will be getting bigger if more is added to it. Okay, so to simplify this step here a little bit, we have 2/3 pi r cubed. And that's gotten from multiplying the 1/3 times 2 is 2/3 pi, there, r squared times r is r cubed. And so now we are poised to take the derivative. The derivative will be dv dt equals 2 pi r squared. The 3 we bring down from the exponent will reduce with the 3 down here. dr dt. So now this is exactly what we're trying to figure out here. dr dt, we know dv dt is 10. We know the radius is 4. So why don't I just substitute everything in here. There we go. R is 4, dv dt is 10. 4 squared is 16 times 2 is 32, so we will have 32 pi. Then we can just divide both sides by 32 pi to isolate dr dt. And since that will reduce, we will have 10 over 32, that will be reduced in the next step as well. And there we have it, dr dt is 5 over 16 pi feet per minute. And again, that should make sense because the units up here are in feet, and a radius is just one-dimensional, so it's feet per minute. Here's the other rate here, minute.